Hey guys, let's get started on our last foray into Newton's laws. Things we've gone over so far are force basics, which include free body diagrams, types of forces, balanced and unbalanced forces. We've talked about first law, which is the law of inertia, things that are acting on one object, balanced. Third law, everything that's acting on two objects, which includes action-reaction pairs and how when two things hit, they have the same force, but what we see is different accelerations. Today, what we're going over is Newton's second, and we're going to talk about what it is. Excuse me there. We're going to talk about what it is. We're going to talk about examples, something called proportional reasoning. We'll do a multi-step problem. We'll talk about friction equation, static versus kinetic friction, a little bit of graph work, and then we'll have an example. So let's get started. First, Newton's second law is that the net force is equal to mass times the acceleration. Okay, this is where the kilogram times mass divided by second squared. This is how we get our Newton. And again, this net force thing, this letter right here, this is called, it's a sigma. It's a Greek letter. And it basically means just the sum of all the forces, the net force or the total force. Most of our problems are going to be relatively simple that we're dealing with here, but occasionally there will be more. So let's get started with a few examples. Okay. So we'll start here. 450 kilogram mass is accelerated. 450 kilogram mass is accelerated at 2.5 meters per second squared. What is the net force acting on us? So in this case, we've got mass is equal to 450 kilograms. Acceleration is at 2.5 meters per second squared. And what is our net force? So in this case, net force is equal to mass times acceleration, 450 times 2.5, and that's going to give us, that'll give us 1,125 newtons. Straightforward. Now, 2,500 kilogram car pushed by two people, each pushing with 150 newtons of force to the right. There is friction. It acts against them with a force of 50 newtons to the left. We want to know what's the acceleration. All right, so now that we have more than one force acting, here's where a process is going to be. Well, 1, free body diagram. 2, list variables. 3, solve for net force. 4, solve problem. So that's what we're going to do. So here's our free body diagram. I'm going to move it out of the way just a bit. All right, we've got a weight force coming down. We've got a normal force coming up. We've got two people pushing, each with 150 newtons of force. You could just put applied force here if you want, but I'm going to put the numbers in just because I can. And we got 50 newtons of friction force to the left. So there's our free body diagram. What do we know? We know that the mass is equal to 2,500 kilograms. Acceleration is what we're looking for. And so to solve this problem, we're going to need to use our Newton's second law. So it's net force is equal to mass times acceleration. What do we know? We know this. We don't know this. We need that. So let's do our net force next. So net force then is the sum of all the forces. Two 150s going to the right, 150 newton going to the left. So we're going to add those guys up just using their directions. So it's 150 plus 150 because they're going the same direction, minus 50, which is going the opposite direction. This gives us a net force of 250 newtons. All right, now we have this. We can turn this, turn that into a check mark, and now we can solve. So then our net force is equal to mass times acceleration. We're going to rearrange this so that acceleration is equal to the net force divided by the mass. I don't know what I just wrote there, guys. Net force divided by the mass. So we've got 250 newtons divided by 2,500 kilograms. And this should be, I don't do quite so well at division in my head. Just a sec. So it's 250 divided by 2,500, 0.1? Yeah, 0.1. And that means our acceleration then is 0.1 meters per second squared. So if you remember, if you've got more than one force, you really need to do the part where you list your free body diagrams. Now our next problem asks, because it's the same thing, but says we're going to double the size of the car. Okay, it's twice as big. So in this case, if it's kind of a little bit of a proportional reasoning. So let's do it like this. So we know that net force is equal to mass times acceleration. Okay. So in this problem, the net force stays the same, but we're going to double our mass. And we want to find out what happens to our acceleration. Okay. So basically what that's saying, this is how I do these problems. Whatever stays the same, that gets the 1. So we've got 1, and we're going to say, what are we going to do? We have 2 variables in here. What are we going to do to the mass? We're going to double it, and we have to figure out, what do I have to do to the acceleration? What do I have to do to that acceleration to keep this a true statement? So solve for A. So that means A is equal to 1/2. So if I double my mass, my acceleration gets halved. So my acceleration, all right, so 1/2 of my acceleration then, that's all over the place, isn't it? So 1/2 of my acceleration is equal to 1/2 0.1. So my new acceleration, 0.05 meters per second squared. What that's saying, guys, is that if I increase my mass, my acceleration has to decrease. This is called inversely related. In other words, this is very much a, if you've ever gone Thanksgiving shopping or big grocery shopping with your parents, and they just keep tossing stuff in, okay, the more stuff you put in there, the slower you're going to go. All right, that's all we're saying. Last problem here. All right, we are going to, I'm going to move this down just a little bit. All right, here's a 2-step problem we're dealing with. We have an artillery shell with a mass of 55 kilograms. The projectile is fired from the piece and has a velocity of 770 meters per second when it leaves the barrel. The gun barrel is 1.5 meters long. Assuming the force and therefore the acceleration is constant while the projectile is in the barrel, what is the force that is acted on the projectile? So let's take a look at what we have in this problem. We know we've got a mass of 55 kilograms. Okay, or actually, let's back it up just a sec. The ultimate question in this problem is, what is the force? So we need to find the net force acting. We know that net force is equal to mass times acceleration. I have this. My mass is 55 kilograms. Okay. but I don't have my acceleration. Okay, so I got to find that. So that means if I have to have my force and I need my acceleration, from everything I'm looking at, I've got 770, 150.5 meters long. This is telling me that my acceleration I can solve as a kinematics problem. So let's figure out what we have there. So we've got projectiles fired from the piece, and it has a 770 meters per second velocity when it leaves the barrel. So that means my final velocity is 770 meters per second. I have a delta x of 1.5 meters. And I think, is there anything else that we need? One more piece of information. Considering it's fired, I'm going to say that tells me that my initial velocity is 0, because you don't fire something when it's already moving. So there we go. So now we have two problems. We have first our kinematics problem, and then we're going to have our force problem. Okay, based on the variables that I have here, acceleration, final, x, and initial, the equation I'm going to use is final velocity squared is equal to the initial velocity squared plus 2 acceleration times delta x. That goes away. So our final velocity squared divided by 2 times delta x is equal to a. So 770 squared divided by 2 times 1.5 gives us an acceleration. Beep, beep, boop, boop, beep. Let's check this out. 70 times 770 divided by 2 divided by 0.5. Try that one more time. 770 squared divided by 2 divided by 1.5. So that gives us an acceleration of 198,000 meters per second squared. So now that I have my acceleration, I can go back here. Now I have everything I need to solve for my force. Move it over. So my net force is equal to mass times acceleration. So it's equal to 55 kilograms times 198,000 meters per second squared. So we're looking at force of 10,890,000 newtons. Ouch. Ouch, ouch, ouch. That's going to hurt. All right. That's how things get blown up. So that's how you do. I'm all over the place here. That's how we're going to do a double-step kinematics. Basically, you've got force equals ma on one part of it, and then you've got kinematics on the other. Here is another... Okay. So, friction is kind of interesting here. We'll talk about it in class when we get a chance. I'll kind of show it to you a little bit. But the basic idea is that our friction is related to our normal force. Okay, if something is heavier, it has more normal force, and the more normal force it has, the harder it is to change its motion, all right? And because of friction. So what happens is that friction then is equal to a ratio of particular coefficient of friction times the amount of force, okay? So this is friction force. This is in newtons. This is our normal force. And this is our coefficient of friction. There are no units for the coefficient of friction because it's basically a ratio of surfaces. It is the friction divided by the normal force. So this is our this is our primary, and sometimes you'll use it like this. Okay. Other things we need to know is there are two types of frictions. There's static, which is the amount of frictions it takes to get something to move. All right. Keep from moving. And then there's kinetic. The equation is the same for both. It's just that the value of that mu is different. So static keeps you from moving, and kinetic is the force that you need to keep it moving. I think I mentioned just a few seconds ago the entire idea of the kind of grocery cart. I don't know what I just said. Anyway, the grocery cart thing. So think about this. The more you put in to the grocery cart, and all of a sudden mom tosses in a turkey and a ham and a bag of potatoes, okay? And you're not paying attention, and then all of a sudden you have to push the cart again, all right? That's what this is. It's hard to push that cart, right? It's how you push, all right? It takes a while to do it. And then what happens as you're pushing? Suddenly it starts moving. And then what happens? What happens as you move it? You have to slow down. You can't use the same amount of force because all of a sudden you start speeding up. What this tells us is that static friction, is greater than kinetic friction. And this graph, friction graph, always look like this, okay? Where this value right here, this is the static friction. This is the amount of force that you need to keep something from moving. Okay, so you get 75 newtons. And then once you are moving, this is our kinetic friction. Okay. Basically, it's just a graph. This is the friction force versus the applied force. The graphs are always the exact same shapes, okay? Let's try a sample problem. And the way we're going to do it is the most common, is kind of all the steps. They're not really hard, but there's a couple of them. So our problem is that we have a 10 kilogram box. 10 kilogram box. Pulled across the floor at a constant velocity towards the left by a 90 Newton force. We're going to draw a free body diagram, determine the normal force, the net force, the force of friction, and we're going to find the coefficient of friction. So let's draw this out. Here's our free body diagram. We have it's on the floor, so we've got to know that we've got a weight and we have a normal force. Okay, and we know that it's being pulled to the right by a 90 Newton force and that there's some force of friction. All right, things that we also know, we know that the weight is mass times gravity, so it's 90 times 10, so we've got 900 newtons. Okay, so we just drew our free body diagram and we labeled our forces as we know them. Now, normal force, right here, that is in the y direction. So we're going to start by doing the normal force, which is the sum of the forces in the y. Now we say it's equal to mass times acceleration, but in this case, the acceleration is 0, right? Because the box isn't going up and it's not going down. It's staying flat on the surface. So our net force, right, then the forces that we have the normal force going up minus our weight force going down is equal to 0. This means that our normal force is equal to our weight. And we already solved that over here. So our normal is equal to 900 newtons. Next question. So this was B. This was A. What is the net force on the box? All right. Our total net force, horizontal and vertical, is 0. Why? Because it's constant velocity. Remember, whenever you have stuff like this, you want to be able to point to the words that tell you this, because it says constant velocity. So there's our C. Our next question is the force of friction. Okay, that's D, and force of friction is right here, and it's working horizontally. So for D, I'm going to do net force, but I'm doing it in the x direction. And so net force in the x is equal to mass times acceleration. Because it's moving at a constant velocity, that means my acceleration is 0. So my forces in the x direction are the 90 newtons going to the right minus the force of friction is equal to 0. Move this up a bit. And so therefore, amazing as it sounds, friction is equal to 90 newtons. Our last step is E, to find the coefficient of friction. So friction is equal to, coefficient of friction is equal to the force of friction is equal to the coefficient times the normal force. So that means our mu is equal to friction divided by the normal, and our friction is 90 newtons. Our normal force is 900 newtons, which means our coefficient of friction is 0.1. And we're going to add an F. Is it static or kinetic, and why? All right, it's kinetic friction, and we know it's kinetic friction because it's already moving at a constant velocity. All right, that is Newton's second law. Newton's second law is a very practical math-based one. It's kind of like going, hey, I did my Newton's first law. It turns out it's not balanced. There is a net force. And so what do I do now? Now I solve for those numbers. Newton's first and second laws are always on one object. The third law, remember, it always has two. Have a good evening, and we shall meet again in the classroom.